Dzień dobry. Hello. My name is Michał Warda, and today I'll be presenting on DevJS 2025. Very happy to be here again. It's like my third time here, so I hope you'll enjoy the presentation. The title of my topic today is Bridging Speech, Text, and AI Agents and How to Build a Desktop App in Tauri. So, as a brief introduction, around 2 months ago, 1.5 months ago, I was participating in something called 11 Labs Hackathon. 11 Labs is a unicorn working on speech-to-text and text-to-speech models. And me and my team, we've created an application in Electron. It didn't fully work. But the name of the application was Say It, and it was supposed to be an assistant working across the whole system for the user to be able to steer and use their voice to communicate with the computer, with their machine on Linux, Mac, and Windows. And we've created something. Later, we've renamed it to QSpeak and rewrote to Tauri. And I wanted to talk to you about how we rewrote it to Tauri, why we did it, how does it work, and why do we think this is a better solution. So our application, I'm going to demo it briefly, works in this way. Here we have a notepad, simple, and if I wanted to write to it, it's cool because I'm at my desk, so I have both my hands free. But if I was presenting at a conference, I would have a mic in one of the hands and it would be much harder, but I could write something here. But thanks to our application called QSpeak, you can just press one button or a shortcut, and a window will show up. And this window is one of the windows that QSpeak has, which is a transcription window. Essentially, wherever you are in your system, here we are in a browser, but you can imagine in any other application, you can talk to it, and the transcription from your voice will be pasted directly into the application. Another sentence. Yes, so it works perfectly clearly, but this is nothing amazing. There are multiple applications that works this way, even the system built-in transcription. But what if, and this is my only slide that is outside of the application, or I'll skip it for now. But what if we could steer a LinkedIn message, for example, from this assistant? I'm gonna turn on something that we call a persona. I'm gonna pick a marketing assistant persona, and I'm gonna talk to the application and say, for example, hello. And the marketing, hello, yes. And can you write a post? Okay, we have some brief problems with the application with the demo. One more time. Hello, can you write a post about DevJS today? So as you can see, the assistant has a built-in functionality. It can also not only transcribe what we're saying, but it can also do a lot of other stuff, like writing posts for LinkedIn with a lot of emojis and new lines. It can also interpret what is on the screen dynamically. I can say, write a post about what is currently on the screen. Oh, and as you can see, it can also see the screen if I press the take a screenshot button. Also, if I were, for example, in a terminal, here I have a terminal emulator, I could, for example, say, list all directories, including those hidden ones. I can have an assistant that directly transforms what I'm saying into code-based text. But enough talking about how this application works. I'm just gonna, for the purposes of the demo, only for the purposes of the application, also show that here we have a tray icon and different menu options and also different windows. So, for example, here we have the settings window. We also have different windows. So I'm gonna go back to the presentation, and now let's talk. Let's move a step back, and how do we typically go with creating our applications? How do we build a web application? Web applications works in a more simple fashion than a desktop application, but mostly it involves a browser that is running your code, typically written in JavaScript. It's at least running JavaScript later. You can use different languages and compile them to JavaScript. And through HTTP, mostly, there are different methods, but mostly through HTTP, it communicates with a server, and that server runs also distributes the code, etc., etc. And so, for example, here I have the dev.js website. It works in a way that if I'm the user, I click on the page, something happens, very simple. I click on different things, and the events that are handling this application come mostly, not fully, but mostly, to simplify it, from the user using the window, and also the window itself. So, for example, the window itself can have an animation. I don't have to click anywhere to have the application show up, but I need to be on the website for it to be working. And the website itself has to be in the foreground or in the background for some time to be working. And how do we build a native app compared to that? In a native app, there is an app window, as we've said, as I've showed previously. There is, instead of HTTP, we mostly use something called IPC, or Inter-Process Communication layer. It can be HTTP, it can be different layers, it can be a socket, it can be a system socket, depending on the architecture of the underlying system. And we also have the local app server. So it looks similar to how a web application is working, and honestly, building an application like that is pretty similar. So in Tauri, for example, here we have a bit of TypeScript code. It works in a way that we can, or I'll show the Rust code first. Tauri is a engine that on the local app server side uses Rust, and in the app window uses JavaScript or a web view. So essentially, similarly to Electron, it uses which Electron uses Node and JavaScript on the front end. Tauri uses Rust and JavaScript on the front end. So it works in a way that, for example, from the Rust part of the code, I can create a comment. The comment, for example, for retrieving the current app state, I can call this code, retrieve the machine, which is our place where we store the state, and return this machine. So similarly, it transforms into simple JavaScript, get an object, return an object. And on the front-end side, to call this code in the Rust through IPC, we do an invoke, and we pass the name of the function, the name of the comment, and then we can do whatever we want with it. So, for example, set the new state. So this is a simple way to do it. Okay, so this would work like this, pretty simple stuff, but native applications can do much more. than a simple web application. That's why we do native application instead of web applications. For example, native applications can handle multiple windows. Web apps also, but those are different entities communicating with each other. Not often do we, on one system, want users to have different windows with the same application working at the same time, different tabs, etc. Second thing, in our application, we're using something for global keybinds or key shortcuts, which in the web application is impossible to set up, because the only shortcuts that are working in a web application are only the ones that you set up when the user is focused in that window. You can, for example, have audio events, but not through the browser interface, but from different sources, etc. You can, for example, attach a microphone to the audio output from your system to do some funky stuff with audio processing. You can also do image events, screenshots, etc. on all of the platforms. Some of those features are already there in the browser, but not all of them, and it depends on the platform. You can also, for example, like we did, do native LLM local running. You can also have local memory besides local storage or whatever. You can save files directly into the system rather than doing it through the server and saving it in that scope of the server, for example, in the cloud. And one more thing is that the applications themselves can work offline. So if you don't have access to internet, the application still works. So the difference here is then that when you have a native application, the simple one is very similar to the browser application, but the more complicated one is turning out to be more and more complex. I'm gonna increase it a tiny bit, but as you can see, you can have multiple windows running at the same time, connecting to the same server. You can have a connection to a microphone, screen, GPU, other apps. Typically, in web applications, you would have those attached through the browser directly, so through the app window. But for example, if you want to synchronize different windows to be showing the same state from the microphone, you would need to connect it through one window, send it to the server, and from the server send it to another window, which is very processor intensive, takes a lot of energy, etc. So how do we set up in Tauri multiple windows, for example? I'm going to be showing some parts of code written in Rust. If you're not familiar with Rust, don't worry about it. I'm going to highlight only the parts that are interesting and explain it to the best of my knowledge. So, for example, if we were to create a window from our local app server, we can dynamically spawn app windows. And here we can do it by creating something, a web view window builder. We pass to it the URL of the HTML file that contains our web view definition, similarly to Electron. The window name and an app handle, so essentially a reference to the application as a whole. The page refreshed. Give me 1 second. Okay, we're back. We can also pass the size of the window, the initial size, because later we can change it dynamically. We can say that, for example, it has to be centered. It shouldn't be visible by default. So the window is not visible by default. It's somewhere there, but it's not visible. It cannot be resizable, no decorations, always transparent. So we have the window hiding and showing in a nice way, always on top, and we just build it. And then later, we can use this window. So essentially, we assign it to our application, and if we want to later use it, we can just retrieve it, do the get web view window again to not spawn another one. So very simple code here, and this spawns a window and later allows us to change it. So for example, if we were to resize this window, we then have the window reference, and we can show it, hide it, etc. And on this slide, you can see how it's working. So we retrieve the window for passing the app handle. If it doesn't exist, it's created. If it exists, it's returned. And then we, for example, when pressing the open settings shortcut, we show the window, we can set focus to it, we can unminimize it, for example, because sometimes it's minimized, etc. We can also get this window and close it. So whatever you imagine can be done with a window can be done through code like this. So the second part, global keybinds. How do we approach stuff like this? So essentially communicating with the system, not through the browser part, but directly through the system. Instead of only window management, how do we, for example, handle global keybinds? Tauri has something called plugins, and the plugins work in a way that you register them. For example, like here in your code, you call Tauri plugin global shortcut with handler build. So you create a plugin, and later at the bottom, app global shortcut register. You register the shortcut, this plugin. And in this plugin, for example, we check if the shortcut is Control-N. If it is, then we show text Control-N pressed. If it's not, if it's released, if it is this specific shortcut and it's pressed, we show pressed, and if it's released, it's released. We have control over the plugin itself is installed through something we call Cargo. So Cargo is an NPM, but for Rust. You just run Cargo add and the name of the name of the package, and the package is installed automatically into your system, and then later you can use it like so in your application. All of it is documented pretty nicely in the Tauri documentation. You can use those plugins, add them, remove them, etc. The important part and the differentiator between Tauri and Electron is that the convention for plugin creators and the application maintainers is to give the user an option. In Electron, for example, if a plugin is created, it usually works in a way that you can launch it only from the Node.js environment, so the server part or the window part. In Tauri, you can do it from both sides. So there is also, when you're installing this plugin on the backend side, so using this Tauri plugin global shortcut builder, you can also do it in a slightly different way from JavaScript in a simpler way. You just import a register, for example, comment. Here I've changed the shortcut to show you how, for example, you can handle comment or control on different systems, and you pass comment or control Shift-C, and then the shortcut is triggered. Here, as a parameter, you're also getting the event, and the event contains information if it's a shortcut press or shortcut release. Both of those are working pretty nicely. Okay, so yeah, as I've said, all available plugins can be called from Rust and JS. Let's go to another part. So we can already call Tauri plugins. We can create comments. We can write code for the front end in JavaScript, for the back end in Rust. So what can we do more. As I've said previously, plugins themselves are communicating with the native systems through different libraries. But there might be a situation when there are no plugins and you want to communicate with a system and do something funky with it. For example, in our situation, we wanted to create something called audio listening and saving audio to files, transforming it, for example, removing noises, etc., from the audio transcription to have the best transcription possible from the machine learning models. And we do it by essentially calling Rust code directly. So as I've said previously, plugins are Tauri packages, but there are vast amounts of packages for doing different stuff written in Rust for your system, for your computers. One of those is, for example, cpal. Here you can see a view directly from the docs.rs, which is an npm website, but for Rust. You can see the documentation right here. All of the packages are documented better or worse. You would need to know a bit of systems programming to understand fully what is happening here, but it's possible to, for example, initialize an audio stream from a specific device and play it. Then the stream of audio is saved. It can be transferred to front end or to show this cool waveform like so here. Or it can be directly used on the backend, for example, saved in the file or sent to the machine learning model directly. Okay, the important part here is, the important part here is that Tauri itself, when you're calling those invoke functions, it does something very specific, because invoking a function from a front end sends a IPC call to the backend. And if you're returning anything, instead of the application responding to stuff, it creates a eval string, so essentially a bit of code. It creates a bit of code, sends it to the front-end web view, and front-end web view dynamically calls eval on the string, which is, first of all, synchronous and done in the primary view. So for example, like here in our application, if we're sending like 60 FPS, so 60 comments per second with the new audio data to show this funky waveform to the users, it would be too slow to refresh the screen dynamically. So we're using something called channels, which is a socket connection between the front end and the back end, and the communication is done through socket rather than the invoke commands for this data that is constantly changing, instead of doing simple request response. Similarly to how we do in the front-end world communicating with the server, if we have a lot of data, we use WebSockets instead of simple HTTP requests. Okay, there are a few more things. For example, our situation required us to do some image processing, and it turns out that depending on the platform we're in, it's better or worse to run certain image processing parts. In our application, you can do a screenshot, as I've said previously. It shows up here later, and the screenshot, and the screenshot itself, before sending it to the machine learning model, needs to be resized. So we are calling something called a resizer, and the important part of code is right here. For example, when we're on the 64-bit architecture on the backend, we would prefer to enable the AVX2 extension, which significantly improves the speed of image processing for resizing images on specific platforms. So we can do this. We can also, for example, on Windows, certain parts are not compiling fully, so we're using different paths of code depending on what platform you're in, because it turns out that different platforms behave differently. On the web, you don't fully feel it. You're more likely to code depending on the browser type. So, for example, Safari or Firefox or Chrome, which are still very similar and are compatible usually. On the system level, it's very, very different to call a part of code on Linux and a part of code on Windows. It's completely different APIs, code, etc. So you can, depending on what platform you're using, use certain architectures. Okay. The next part that we've been struggling with, mainly in Electron, was passing native binaries. Because in our application, at least, we're calling native language models. So essentially, when you see me talking to the large language model, and also when you see it processing and writing something, it's doing so from my own machine, from the same one I'm presenting from. And the interesting part is that, for example, for large language models, it is advised to use GPUs. And it turns out that compiling for GPUs for specific architectures, etc., is very, 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 very complicated. So different architectures compile differently, etc. So what we're doing is using a bit of external software called Cobalt CPP, as you can see here. And the Cobalt CPP part does a thing that when it's ran, it automatically detects what the infrastructure of the certain machine is and runs the machine learning models depending on it, optimizes it, etc., etc. And instead of rewriting this code or somehow trying to do the same stuff, because it's thousands and thousands of lines of code, we prefer to run this code, run an external binary that is pre-compiled, and use it in our application. We do it through something called sidecarring. So essentially, our application process starts, and when it starts, another process starts, and we communicate with that process, similarly to how I was showing on the graph. And the important part here is that you can do it easily with Tauri. With Electron, we've had a lot of problems embedding the binaries. It was working terribly. But because the external extensions was not fully working for us and closing randomly, etc., and we had problems building it. The important part is that it's more of a handling this sidecar correctly. That is the tough part. For example, if your application dies, you need to ensure that the sidecar also is shut down, and it's on your it's your responsibility, because for some reason Tauri creators didn't want to handle it. Okay, and another part which is pretty important when you handle native binaries is that it turns out that a .exe file is not working on Linux or Mac, which is pretty obvious when you think about it. But for me, a person that's not so fluent in native applications, rather just serving everything through the web. It wasn't that obvious. So if we have a binary, we have to compile it first, or download first a compiled version for all of the platforms. And then as the binary is there, we can use this binary inside all of the built versions. I'm going to talk about two features more. First, the local memory, which is very simple. You do it very similarly to how you would do, for example, a local storage part. The only interesting part is that instead of storing it in a browser, you usually store it as a file on the system. So if you want to handle things like encryption for the file, you have to do it yourself. If you want to, for example, when the application is uninstalled, also remove this file with the memory, you have to do it yourself. If you want to, I don't know, handle this, the possibility that the user remove this file because they, I don't know, did something funky on their file system, you have to handle it yourself. As I've said previously, there is a part called distributing. It's not that simple to create an application for a website. You just compile it, maybe even don't compile it and send it through the server to the browser. You have to usually have the server running, but that is then like trivial part. You just write a bit of code and run it on the server. And a compiled application, depending on where the application is running, you have to first compile the application for this specific platform. We've chosen desktops, so Linux, Mac OS, and Windows. There are different versions of Windows, so you have to compile different versions. There are different processor architectures on Windows. So for example, if you want to go with Windows for ARM Windows, you would need to compile a version for that. And also if you're going with a Windows x86 64, so 64-bit architecture, you also need to compile for that. Similarly, for Mac OS and for Linux, it's even more complicated because Linux can be everything, and it can be there can be like 5 different package managers through which you can then install this application. So not only do you have to compile it for a specific architecture, you also have to bundle it. In each of those architectures, you need to bundle for each of those distribution systems. So essentially, if you want to do it through the system, my application. If you want to do it correctly, there's like a bazillion versions that you have to build. And how do you build it? How do you do it? Because it turns out, again, it's not that simple to create an application and later, so to just launch a bit of code from your system and everything works. No, it turns out that it's more complicated because usually when you want to compile for a Mac, you need to do it on a Mac. If you want to compile it for Windows, you usually, if you want to use, for example, GPU acceleration, you need to do it on Windows. If you want to compile for Linux, usually you would prefer to compile it for on Linux. And if you want to compile for x64, 64-bit infrastructure, you need to do it on the 64. And if you want to do it on ARM, for ARM, you need to do it on ARM. You can cross-compile. There is something called cross-compilation. But if you're using native add-ons, for example, as I've said, GPU acceleration or similar things in your code base, in your code, at least for us, we didn't manage to set it up properly. So we do something called multi-compilation using a service called Crab Nebula. Sorry, Crab Nebula Tauri. We're using the service which gave us a explanation of how to do it on GitHub Actions. And we're using GitHub Actions, just give me, we're using GitHub Actions like so, where we have a working workflow that does it on Ubuntu, Mac OS, and Windows, and different architectures. So we create different containers, and on each of those, we're building the application, getting the binaries, and then distributing them, or we will be distributing them. So it's not as simple as having your code running on the server, which is a bummer. Okay, the next part is error monitoring, but because it turns out that if you have a user that is calling your application through the internet, it's much simpler for the user to be giving you information about what went wrong. So usually, if the user is always connected to the internet, you can just set up a server endpoint or use a service like Sentry, whatever, to gather all of the errors. In native applications, it's similar, but not so trivial. We need to handle, for example, a situation when the user is offline, support when they have a problem, when they reconnect to the internet, then send the errors, so store them in a file and send them when the user is reconnected. Obviously, it can also happen in a browser application, but usually when you have a browser application, the user does you don't handle the situations when the user is not connected to internet fully, at least in the most applications. We're using something called Sentry Tauri, which handles all of those situations. It's pretty trivial. You just, similarly to how you would do on in a typical backend application, you set up your client. It automatically attaches a bit of Sentry code to all of the web views that are there. So, for example, if you have multiple windows and one of them fails, you don't have to set it up for all of the windows. It handles it automatically, and it also handles the main Rust process. If the application fails, it creates a snapshot of this application and sends it also with the error. And updates. As I've said, we were using something called Crap Nebula, or will be using something called Crap Nebula, and it works in a way that it handles the distribution for us. We essentially, similarly to how Firebase works, distribute the native binaries to the service. It itself later publishes it to everyone. And you can also do dynamic updates, etc., all through this service. It's not as simple as in Electron or in WebView or React Native, because parts of the application, not only in React Native, but in WebView applications, pure WebView applications or websites, because parts of the applications are compiled. And compiled code usually cannot be hot swappable, so you cannot just click refresh and it works. And code is not distributed always because the user doesn't always connect to the server. So the updates are a bit harder. Sometimes you need to haul a whole new binary, or sometimes you need to send partial updates, install them, and, for example, trigger an app restart if you want to have everything working correctly, because the native code is not hot swappable. Okay, so just a brief summary of positive and negative things between Electron and Tauri. I didn't mention it previously, but why we've resigned from Electron, because the first version of the application was written in Electron. I will say it right now. First of all, the app is snappier. so works a bit better. It's hard to describe. We've tried to measure it, but essentially the lag in an Electron app is about tens of milliseconds for certain parts of the application that we've wanted to handle. In the Rust-based backend, it's milliseconds. So essentially, an update to the application takes around 2 milliseconds, which is why we can get, for example, 60 FPS applications without a problem for processing the audio data, which was non-trivial in the Node version of the application. So we had to write native extensions, which turned out that we have to write in Rust or C or Go or whatever. Anyway, second of all, app builds and actually works on all platforms. The biggest problem we've had with Electron is the app not bundling correctly when we were attaching native code to it. So for example, if we were to attach the large language models, etc., because Electron does a lot of funky stuff, funky optimizations, etc., the binaries were converted in a way that they were not recoverable. There are issues in the Electron repository for it since like 12 months ago, and no one is doing anything about it. So unless you want to write custom code for the bundling applications, at least we didn't have any success in working with Electron on platforms after building. In development environment, everything was working perfectly. When we were building the application, the final build wasn't working correctly. The third part is way less RAM usage. Our Electron application took around 1 gigabyte of memory when it was when it was not doing anything, just working in the background. Our Tauri application takes around 70 to 100 megabytes of memory when it's working in the background. And we need the memory for local machine learning models. Like 900 megabytes of memory is already enough to run the best transcription models on the market. So each megabyte is pretty important. And we wanted to use Tauri because of that. So the smaller bundle size is also a thing, but we don't care about that very much. It's more about the RAM usage. And the distribution of native packages is easier, and the compilation is smooth and does not fail randomly. But there are also some downsides. First of all, the docs for Tauri are bad/terrible. In some places, it feels like the person that was writing the docs never used their own code. And you can feel it sometimes that maybe it was generated or whatever. The most typical like use cases are not documented at all. It's very vague, etc. Second part is community is way less responsive. On Electron, you have Discords, you have like the issues, etc. Different groups. Everyone like is very talkative. Sometimes even too much. In the Rust community, because it's way smaller, you have to wait a lot of time before you get any answers. The third part is the lack of libraries for Tauri. As I've said, you have to write wrappers for some native stuff. It's okay, but sometimes it feels like it's impossible that no one had this problem. I just feel the community is not used to sharing their code as much for the system-based stuff rather than for the web-based stuff. Fourth part is terrible, is compilation takes ages. I have a pretty beefy computer, but for example, for my colleagues, sometimes it takes like 5 to 10 seconds or even 15 to 50 seconds or more to get feedback for their IDE about what is going on, what functions they can use, etc. Because Rust is doing it all in the background, and sometimes when you're using certain libraries, those libraries take a lot of time to compile, and Rust is not super smart about compiling only the required part of code, so it sometimes takes ages. And collecting errors is harder, as I've said, because it's not only Node. The last part is Rust is much, much harder, at least for me, to write code in than Node. Certain parts of code are just very, very complicated, and the model of writing code is also complicated. Okay, that's all for me. Here you can, if you're interested in trying out QSpeak, we're going to be launching a alpha version pretty soon. We want to do it in like this or next week, hopefully. But in the meantime, if you're interested, you can go to our waiting list. And if you register through this link in the upcoming week before the application alpha version is released, we're going to be giving away 2 months of the application for free. So that is it. And thank you. Are there any questions? I'm gonna leave it on this slide, maybe someone will. Was it difficult to start with Tauri? It was very difficult. I mean, the first part, launching the first part of code is very, very easy, but, and Tauri itself as a framework is pretty easy. But learning enough Rust to understand that, for example, if you have a shared state, you need to create mutexes, arcs, etc., because you need to, if you want to call the same object from 2 different places in your applications, you're good luck. So it's harder to learn Rust than it is to learn Tauri, though the documentation is not perfect. Hope that answers the question. Tomek, did your team consider Flutter? Yes, we did consider Flutter, but Flutter has exactly 0 LLM binds, or close to none. We could use, as I've mentioned here, like foreign binaries also in Flutter, but we didn't want to do it for everything. And the amount of libraries written for Flutter is very small compared, I mean, for our use cases, we would need to do a lot of bindings for the functionalities we wanted to use. But besides that, I have a bit of experience with Flutter. I would love to write the whole application in Flutter rather than in this framework, but we needed the bindings. Yeah. Okay. Any more questions? O, jakie są główne zalety w porównaniu do innych frameworków desktopowych, takich jak Electron? Okay, as I've said here, the RAM size, the bundle size, for us, the bundle size doesn't matter like that much because the user will download like a 5 GB model to run locally anyway. So the fact that they would need to download a 700 MB binary for the application or a 5 MB binary doesn't matter probably for our end user, but the RAM usage is crucial. The speed of the backend part of the code is crucial for some application. If, for example, you're doing some audio processing or stuff like that. Right now, you can launch a lot of code in WebAssembly in Node, but still it's not working as efficiently as it is in Rust, native Rust. For us, the coolest moment when we were rewriting the application from Electron to Rust was when we've made the audio graph appear again. It was so much smoother because in Node we were able to do like 15 FPS on a built application for the audio graph. In Rust, it's pure 60 FPS, and it just feels so much better to display this data. And we feel that the users that will be using will like that. So it's mostly efficiency, and it works. The compilation works. Hope that answers the question. Any more? Okay, so if there are no more questions, thank you very much. I'm very happy to have been presenting again. Hopefully see you maybe at another conference. Thank you for the organizers, and thank you for everyone that was here. If you'll have any questions, you can hit me up on LinkedIn, on Twitter, on I don't know, Discord. You can join our Discord and ask any questions you would like, not only about the project, but also about the technology. Thanks a lot. See ya.